Now, so far, we've been concentrating on one end of the electromagnetic spectrum. We've been looking at X-rays and at gamma rays. What other parts of the electromagnetic spectrum are useful to us? Well, ultraviolet and visible and infrared, we know they're not so good. Microwaves, well, they heat us up, but radio waves, we know we're reasonably transparent to those, so maybe we can use radio waves to look inside our bodies too. If we're going to do that, we need to make ourselves interact with them a bit. One way of doing that is to make ourselves a little bit magnetic. And if we're going to talk about how we make things magnetic, we need to talk about something called the X factor. Physicists have got this fancy thing which they call magnetic susceptibility. And they use the symbol X for it. And if you've got the X factor, then you're attracted to a magnet. And if you're not attracted to a magnet, then you haven't got the X factor. So there are no prizes for telling me which of these three materials has got the X factor. If I were to take a lump of steel, got a couple of lumps of steel here, and bring a magnet close, we know they're attracted. They've got the X factor. However, grapes and blue tack don't behave in the same way. They definitely haven't got the X factor. Their X factor is 0. Well, that's almost true. I've got some blue tack, I've got a grape, and I'm hopefully going to show you that if I bring this magnet close to the grape, it is actually magnetized. Here we go. Bring the magnet towards it, and the grape is pushed away. And the blue tack does the opposite. It's attracted. And I can try and slow it down and attract it this way. In fact, everything can be magnetized, even our bodies. They're magnetized because they've got charged particles that are spinning around in some way within that material. If we put our bodies inside a huge magnetic field, like the one you have in a scanner like this, let me just show you what's inside it. There's a huge electric current that flows around the outside of this thing, and it creates a whopping great big magnetic field. If you put your body inside that, you will become magnetic, partly because you contain spinning charges, some of which are protons, and they're the ones that interest us. And what we want to do is to start to play around with these protons and flip them so that they align and anti-align, they flip upside down inside our bodies, because that way they're going to tell us where they are. How do we do that? Well, actually it's quite tricky, because playing around with spinning things and trying to flip them over is harder than you might think. Let me see if I can show you the problem. Over here I have got a little spinning top. There's the spinning top. And it wants to be flipped over, and I'm going to move it close to the top of this huge magnet, and I hope you'll see it wants to flip over. But when I start spinning it, the story looks quite different. So I'm going to put it to the place where it wants to flip over. And now, because it's spinning, the magnet can't flip it over. It's doing the right thing, it's pushing in the right direction, but the spin stops it from being flipped over. So it has to hover there. If we want to flip over something that's spinning, we need to be a little bit more ingenious. Let me see if I can illustrate that. Stephen, this is your moment of glory. Come to the front, and if we could have the freely rotating chair, please. That's great. So in a moment, I'm going to give Stephen a spin in the form of this bicycle wheel, rescued from my wife's bike. She still hasn't noticed. I'm going to give Stephen this spinning object. Let's spin it up. Hold it above your head, like I said. And now let's try and knock it over. So put it down. And you can see that as he moves it down, he starts to move around. If you lift it up, Stephen, you'll stop. Move it down again. You'll start to spin around again. So if I was trying to knock over this spinning wheel, I'd have to wait until it came round, and I'd have to give it a knock. And then I'd have to wait till it came around again, and I'd have to give it another knock. In fact, I'd have to keep knocking at just the rate it likes to be hit at. And that's called matching its resonant frequency. Thanks, Stephen. You've done a sterling job. A small round of applause. And this process of hitting things at the frequency they like to be hit at is called resonance, This bar, for example, likes to be hit at a certain frequency so that it will oscillate this way. If I can hit it at that frequency, it will sing. I'll try and do it. How do I know what frequency to hit it at? Well, I don't have to. I just drag my hand across it, it starts to vibrate, and my hand ends up juddering at just the right frequency. And that's a trick that all you woodwind players know very well. You don't have to know what frequency to blow for a particular note. The rate at which the sound bounces off the bottom of the instrument determines the frequency with which your breath is interrupted. That's a shorter time scale and therefore a higher note. And I want you to think about the magnetization in our body as being like a sound coming from the body. So when we hit this magnetization, which is we'll think of as just a sort of an arrow pointing upwards, if we try and topple it over, we know it starts to spin round, but if we keep hitting it at the right frequency, it will go through this merry dance. And I want you to think of that as being the magnetization singing to us from the body. So we'll put our patient in the scanner and we'll make different parts of the body sing at different notes by making the magnetic field stronger at the head than it is at the feet. So now we've got different parts of the body singing different notes. So we can get a signal from different slices within the body. If we just focus on one slice, we want to see the detail within that. We put another magnetic field that varies from left to right, and now these individual lines of magnetization start singing a chorus of different notes. And so we've built ourselves a way of squishing all the information in this slice into a series of points. That's called a projection. And we know what to do with a projection. We can build a 3D image from it. And we get images, beautiful images, from scanners like this called magnetic resonance imaging. This is a picture of the knee, shows wonderful detail around the joint there, the kind of picture that you want to take of a football injury. This is a picture of the arteries in the brain, here showing a brain tumour, and this is a picture of the heart, and you can even see the turbulence of the blood in the heart as it beats.